So at this point, let me rewrite two equations for you. I'm going to copy these two equations because eventually these two equations are not telling you any information, right? Divergence of E, divergence of H is equal to 0, nothing to be solved. So in the end, all that we care about is how these two equations are interrelated. So this is equation 1, this is equation 3. All right. What do we have to do to be able to solve E or H? Now, you really have to ask yourselves, what have you learned in the beginning of this semester? Is this entirely new to you? One student is laughing. He still remembers transmission line. Well, somehow I believe you all returned the contents of transmission line to me. This derivation procedure is identical to what I covered in transmission line, right? You only have to change E to voltage and I to current. Really, everything is the same. Okay? So now the first equation is telling you somehow when you're trying to solve for the E field or the voltage, E field or voltage is linked to the H field or current. So this single equation, already you have to deal with two field quantities, which we don't really know how to solve. And the second equation, the third equation, is telling you how H field and E field are intercoupled, right? When we deal with time-varying fields, E fields and H fields are interconnected. They are coupled together. So you cannot easily solve one field. But the nice thing is we have two field quantities, E and H, and how many number of equations do we have? 2. So it's okay. It is possible. So we usually first start with Faraday's law. Okay. How should we start? Again, I mentioned this. We performed this derivation 10 weeks ago, or 13 weeks ago. I know 1 week for you is 1 year, but please just tell me, how do we plan to start to solve it? Well, we know curl of H, we know curl of E. Can we convert this one to the time derivative of curl of H? If this is becoming curl of H, I know it, right? I already know curl of H is related to E. So if I can replace this H by curl of H, then I have E and E on the two sides. Then I'm solving the same field quantity in a single equation, right? That's exactly the same procedure we used in deriving transmission line. So all we have to do, if we want to convert this guy to curl of H, making a time derivative, all we have to do is take curl on both sides, right? Well, taking curl on both sides, double curl of E, we also covered this. This is the definition of the vector Laplacian. Right? Left-hand side because we're taking the curl on both sides, so on the left-hand side, we have double curl of E. And double curl of E, by definition, is the gradient of divergence of E and minus the vector Laplacian of E. So looking at this side, the left-hand side, can you tell me why all the textbooks are trying to make the simple medium charge-free? Because we want to simplify the derivations. Divergence of E is 0, right? So all the textbooks are trying to help you, right? So all the assumptions are really useful. Otherwise, your derivation becomes complicated, right? Left-hand side, you have this negative vector Laplacian remaining. On the right-hand side, so look carefully. Each step requires your understanding to the assumptions to the material. Curl of this entire thing in the parenthesis, negative mu h time derivative. Here, I have pulled this mu out of the curl, right? So now I can pull negative and mu out, but can you tell me why? Which assumption have I invoked so that this mu can be pulled out of the curl operation? Now, what is curl? Curl, you have to perform spatial derivatives. And also Laplacian, also divergence, also gradient. So you can pull this out easily because, say out loud, which assumption are we now invoking? You have all the three assumptions before you, right? If your material is inhomogeneous, both epsilon and mu are also functions of space. They need to participate in the curl operation, right? And you have chain rule. So if this is mu of R, you have to perform the curl on mu. You also have to perform curl on H, right? That is going to make your derivation extremely messy. So now you can pull this guy out because, hey, in the very beginning, we are only dealing with the simple medium. So here, we have used the fact that we are dealing with a magnetic homogeneous medium, right? So this mu is a constant everywhere. For each location, you have the same mu. All right, so finally, we have curl of H on the right-hand side. That's what we want, right? Why? Because we already know that curl of H is somehow related to the time derivative of the E field. So now, just by replacing curl of H by this initial modified Ampere's law, left-hand side is E-related, the right-hand side is also E-related. We only have one single field quantity. Then we can solve it. Okay? So in the end, that's what we have. So this is already called the wave equation. The wave equation in a simple medium. And because the fact you have this partial differential equation, and over to the right you have 0, meaning you have no driving source. So this is called the homogeneous wave equation. Have we learned this before? Actually, we did. This is, just by replacing E by voltage, This is something we learned in the past in transmission line, okay? Now, can you tell me, what did I do to convert from this to this? This is assuming in free space. So we performed all this derivation for simple medium. If I want to go back and ask how this wave is propagating in vacuum, do I need to repeat all the derivations? No, because the vacuum is the most simplified medium. All we have to do is convert to this one. But you have to ask yourself, I mean, what type of transformation did I perform? What is C? What is C? This was covered in the first PowerPoint set, okay? After 14, 15 weeks, again, can anyone tell me how the speed of wave in vacuum is defined? I don't want to give you pressure, okay? Right? The multiplication of mu 0, epsilon 0, you take the square root and you invert it, okay? So what is mu epsilon? Mu epsilon is mu r, epsilon r, mu 0, epsilon 0, right? Right? So this is mu r, epsilon r over c squared, right? You change this one and you square it. So all that I changed is mu times epsilon is equal to this one. But if now I want to convert back to vacuum, this mu r equals 1, epsilon r equals to 1, right? That's all. So this is becoming 1 over c squared, right? But basically, what I'm telling you is you have to understand and be able to learn what this equation is teaching you. This equation is telling you this E field, well, if you have a propagating E field in certain simple medium, can you directly tell me what is its propagating behavior? Wave propagation behavior are described using what terms? If you have a wave and you want to really quantify it or describe it, how would you describe it? I have wave number 1, right? I have wave number 1, and I have wave number 2. What's the difference? Waves can propagate with different speed and direction. Okay? So you really want to capture a wave using 2 parameters and direction. Speed or velocity and direction. That's all you need, right? So what message is given in this time domain homogeneous equation? Which or what information are provided here? Think about it. if you have a propagating wave, then basically, this is what we covered. We have a mathematical form of a function of time, and if it's one-dimensional, propagating in z, then you have the speed, right? So basically, this guy, mu times epsilon, is the inverse of speed squared. Okay? So this time domain equation, time domain, tells you how fast this wave is propagating. If you want to know the speed or the magnitude of the velocity, you need to have time dependence. Okay? All right, so magnetic field follows the same procedure. It's entirely basically similar, but now you have this relation. So can you tell me, or tell yourselves, what information is provided in this wave equation? This is the same homogeneous wave equation for the simple medium, but now it's only telling you the H field. But what information, what additional information is provided for you? If you compare to the previous one, in a simple medium, where you might have propagating E field and H field, do you have different propagating speed for E field and H field? No, they propagate at the same speed. Okay? So that's a nice thing. So you have two classmates, and you walk together to the cafeteria to get lunch, but one guy is tall, one guy is short. So even though you're walking with the same pace, but one guy is propagating faster, walking faster. That's not the case for the so-called electromagnetic waves. EM waves have E field and H field. They always walk together at the same speed. So this equation, together with the previous equation, tells you that these two fields are excellent friends. They never walk by each other, right? They always walk together. Same velocity. But here you don't really see the velocity. I would prefer speed. Okay, you don't really see the direction. And if you still remember, this is what we covered for transmission lines, right? Voltage is a wave. Current is also a wave. They propagate together with the same speed, right? Now, you can no longer tell me you don't remember, because I'm trying to give you back all the memories lost. This is what we solved for the lossless transmission line, right? Voltage is a wave, current is a wave. They both propagate with the same speed. Now that we're trying to extend to three-dimensional waves, the only difference is in transmission line, we only have a single propagation direction. So we have this twice partial derivative to z. But now, this wave can propagate in x, y, or z directions, whatever direction. So that is changed to a vector Laplacian. Vector Laplacian for only the z direction is exactly this one. Okay? So if you have the scalar wave, right, transmission line, all the analysis can be performed using scalar analysis. So that's easy, approachable. And here we have learned, well, the velocity is 1 over the square root of LC, right? This two multiplication. Now you have a vector wave, the same. The velocity is 1 over the square root of mu epsilon. Okay? So basically, we came back to learn propagating waves, which was covered in the very beginning of a class, but somehow extended the vector features. Okay? Okay. Questions for you to ask yourselves during the weekend. Here we have really assumed very, very simple medium. Okay? Linear, homogeneous, isotropic, and source-free, charge-free, and current-free. Now, what happens if one of these 5 assumptions is no longer valid? How would you modify your wave equation? This might appear in your final examination on June 22nd. Okay? Any one assumption being revoked, you have to modify your wave equation. Okay? Right? Median is complicated. But now, take a look of these equations. Over to the right-hand side, you have 0, meaning the physical meaning is you don't have any driver. You don't have a source. So this is asking, you see a lot of chicken running around eating all this grass, but you never ask where the chickens are from, right? So the egg is coming first or the chicken is coming first? Right? The same question we should investigate into. Here, it's only telling you you already have a wave. You already, in the space, you already have some propagating wave. But this equation cannot really tell you where this wave is coming from, because over to the right, you have no driving source. Okay? So think about it. Next Monday, we are going to talk about how to create propagating waves. But of course, first we have to deal with the time harmonics, the phasor notations of the wave equation, which is called the Helmholtz equation, right? So try to pay attention to the physical meanings that you can learn behind the equations. The derivation procedures is pretty much the same for Helmholtz equations, but the meaning behind the resulting equation is different, right? So next Monday, maybe we can finish everything. So next Wednesday, you can just enjoy your earned extra holiday, right? See you next Monday.